Okay, this is lab 4 for Physics 2212, and this lab is about circuits. So the purpose of the lab is to predict and measure potential difference in conventional current in circuits. So we're going to use resistors and capacitors to model different circuit setups, and then to do the calculations, we're going to use the energy and current conservation principles. So specifically, we're going to understand resistors in series and in parallel. We're going to measure the conventional current and potential difference, and model circuit behavior with resistors and capacitors. The overall result was that the simulation modeled the expected outcomes of the circuits according to the loop and node rules. So our physics principles are first Ohm's law, which just states that voltage equals the current times the resistance. We're also going to use the fact that capacitance equals the charge divided by the voltage. And our overarching principles are the loop and node rules. So the loop rule states that the total potential difference at any point in the circuit is 0, and the node rule states that the current flowing into a node equals the current flowing out of the node. So the procedure, we used a circuit construction kit and dragged and dropped batteries, resistors, capacitors, and then used wires to connect them, and used the ammeter, voltmeter, and chart tools to collect and display data. And we repeated these steps for a variety of different models. So the first setup we have is this top right picture with two 1.5 volt batteries and then two different resistors of different resistance. We would predict that the current equals the total voltage over the total resistance, which is 0.02041 amps. And when we connected our ammeter, we got 0.02 amps, so as expected. When we reversed that ammeter, we got negative 0.02 amps, also as expected, since the current was flowing in the opposite direction. Next, we used a voltmeter, as you can see in the bottom picture, to measure the potential. So at the battery, the potential was 3 volts, and at the resistor, it was 0 volts. And this is because the circuit is still open when you're connecting it using the voltmeter, because the voltmeter has a lot of resistance. So to continue on with that, we measured the potential difference at all the different points as shown in the picture below. By loop rule, we would assume that the sum of the potential differences is 0. And that is true because we have 3 volts, negative 2.04 volts, and negative 0.96 volts, which equals 0. And you can see in the upper graph where that distribution is. And the slope goes down when you're going through the resistors. Again, it's important to note that the voltmeter does not close the circuit because it has high resistance, but the ammeter does. Next, we replaced the voltmeter with a second resistor with 100 ohm resistance, and the ammeter reading went up to 0.06 amps. And that's because less current will go through the resistor and more current will go through the ammeter because that has less resistance. Here are the resistance calculations, again using Ohm's law. So we see that the resistor of 47 ohms gives a 48 ohm resistance. The second resistor has 102 ohm resistance. The wire and the ammeter both have 0 because they have no voltage going through them. Our next setup was an RC circuit. So we connected a battery, a bulb, and a capacitor. And when first connected, the bulb is going to be at maximum brightness, and then it's going to fade over time with exponential decrease. If you disconnect the battery and connect the bulb to the newly charged capacitor, the bulb is going to shine steadily bright as shown in that picture below. So the next thing we did was measured the time it took to charge and discharge, both for a 10 ohm bulb and a 20 ohm bulb. So as you can see, for the 10 ohm bulb, the charge and discharge time was about 20 seconds, and for the 20 ohm bulb, it was about 40 seconds. So from this, we can tell that resistance is directionally proportional to time. Next, we took measurements as the capacitor discharged. So using the proof that was shown in the lab document, we know that the ln of the the voltage divided by the initial voltage versus time gives us the time constant. So the time constant is just going to be equal to the slope, which is -1 over RC. So we can solve for the slope and see that it's 5.924, and that's going to be in seconds. And so the expected outcome would be 6 seconds because we know that it's just the resistance times the current, so 30 ohms times 0.2 farads. So you can see my data I collected as well as the graph with the slope. So wrapping up with the reflection questions, both of these have similar answers. So if we replaced or if we did this lab in real life rather than this ideal model, the actual ammeters would not have zero resistance. So some current would be blocked as it flowed through the ammeter, and this would lead to slightly lower results. Similarly, if we used a actual battery in real life versus the model, the bulb would not charge or the system would not charge instantly. In real life, it takes some time to charge because the resistance isn't actually zero going through a battery. Thank you.